So, good morning. This is the introductory lecture of Controle em Espaço de Estados. I think that the official name is Linear and Nonlinear Multivariable Control or something like that. And this is going to be presented in English because we have a number of foreign students that I welcome. My name is João Miranda Lemos. I'm the responsible for the course. You can see here my contacts. These slides are already published in Phoenix, so you can find them there, or you can find my contacts at the general information or the web page in Phoenix of this course. And the team that is going to present this course is made by myself. I'm in charge of theoretical lectures, and Professor Pedro Batista, that you can also see here his picture and his contacts, and he will be in charge of the lab. So concerning lab problems, you should send an email to him. Now, what I want to do today is to present you a number of practical things concerning the course. And of course, these practical things concern where do I study from, or what is the evaluation method. And then most of the time we will devote our time to give an idea of what is the course about. So where can you study from? Actually, in this case, it's very easy. You have plenty of good stuff to study. And I've listed it here. So you have slides. These slides are divided in 4 parts corresponding to the 4 main parts of the course. And you have problems. There is someone who should disconnect the microphone, please. We have problems that are published in, thank you. We have problems that are published in Phoenix. And actually, we have 2 types of problems. We have a series of problems that will be more or less covered in a systematic way in the practical lectures, as aulas práticas ou problemas. And we have also other problems for self-study. And in addition, you can look in previous pages of previous editions of this course in Phoenix. All of them are open to the public, and you can find them previous exams and previous tests, most of them with a solution published. Here and there are some mistakes, misprints or miswritten things, but I'm sure that the material is pretty reasonable. Then there will be a lab guide, also published in Phoenix. All of this is already in Phoenix. And I wrote a book published by IST Press that covers completely the course, where you can find the texts, so continuous text, not slide type texts, that cover all the course with problems, solved problems, unsolved problems. And, at this moment, it's impossible to go to a bookshop to buy it, but you can get it from the virtual bookshop of IST Press, and I've included here a link to their page, and also to a number of from a number of other virtual bookshops that are listed in this page, including FNAC and Bertrand and others. This book is in Portuguese, although the slides are in English. But if you, the problems are mostly in Portuguese, but many exams and tests where you can find many problems are in English, and the solutions are in English. And for the foreign students, you also have this book, Franklin and Powell, which covers a lot of material, but it's non-exhaustive. So, but with the slides, it's enough. Okay. In the slides, I included some information to synchronize, to indicate the pages of the book that correspond to those slides. Okay, so it's, you can make a, you can guide yourselves having a kind of roadmap in the slides and reading the text in the book if you wish. Now, about evaluation and grading, we have two components, theory and lab. And for theory, we are going to have one exam, and this exam is offered in 2 dates. You can go freely to each of them or to both, and it counts the best grade. So if you just go to one, it's okay. If you go to the first one and you get, say, 19, that's an example I like to give. You get a 19 in the first exam, and you want to improve your grade to try to get a 20. But then you go there and you get a 12. Okay, your grade will be 19. Okay, I'm joking a little bit with you. The approval requires that
Professor.
Yes.
Just one question. In Phoenix, it says we have 2 tests and 1 exam.
In the you mean in the dates?
Yeah, exactly.
That's because GOP has not yet changed it.
Oh, okay.
Okay. So, but if you look at the method of the evaluation method in the tab, it is written how it is here. I will send you, let me take a note. I will send you the dates of the exams. By the way, these dates have been settled by your delegates. Okay, I will send you an email with this the dates of these 2 exams.
Okay, thank you.
You're welcome. So the laboratory, you have to do one work. I will speak a little bit in a moment about what is the subject of the laboratory. And you have to write a report in groups of 4 or 3 exceptionally. But the grades are individual. There will be a discussion which is individual about what you have done, a small discussion in the last lecture, in the last lab session, and the grades will be individual. And the final grade is 7.7 times theory plus 0.3 times laboratory. Any question? Okay. I can't see when you raise your hands because you are too many. Let's see how many we have here. So we have 88 students, which is not much because we have almost 140. So more than 50 students are not attending this first lecture. So I can't see your raised hand. So you just say professor or please or something. Or if you want to speak in Portuguese, you can speak in Portuguese. Okay. So If it is important, I will translate what you are saying, if you don't feel comfortable speaking in English. Okay, let's say something about laboratory. Let me change for a moment the okay, you can see my slide, isn't it? Slide number 6.
Yes, you can.
Yes,
Okay.
you can.
So what is the objective? The objective of the laboratory is to design and test a state feedback controller to equilibrate an inverted pendulum. Okay. Now, we have one difficulty because this year, maybe we don't know yet, but at least in the beginning, the work has to be made virtual, so by software. And the guide is organized in roughly 2 parts. The first part, in the first part, you design and test everything in software using MATLAB and Simulink. And in the second part, you test on the real plant. We have, you can see here a picture of this inverted pendulum. I will show it to you working. Okay, let's see it working. Can you see the movie? Are you seeing the movie?
Yes.
Yes.
Okay, so the idea, well, here this is sweeping around. The idea is to keep it still. I made it sweeping around because otherwise the movie is very sad, because it's just a stick in the vertical, moving very little. Okay, in this way we move it from one place to another, and that creates some disturbances. Okay, so let me stop this stuff. Okay, so you are going to receive a linearized model of this inverted pendulum. Okay, this is interesting because this is a unstable system. I mean, you have an equilibrium, which is the pendulum perfectly vertical, but if you disturb it a little bit, it will move away from the equilibrium. Okay? In this course, one of the things that we are going to study is a precise notion of stability for nonlinear systems. And this is a nonlinear system because when you deviate from the equilibrium, you have some forces that depend on the sine or cosine of the angle, depending on how you measure the angle. So this is actually a nonlinear system with multiple equilibrium points. You have, of course, one point which is the pendulum upwards, and then you have an equilibrium which is the pendulum downwards. So you have it up, and you have it down. Okay, and actually you can turn it for multiples of 2 pi. So again up and down, again up and again down. So you have an infinite number of equilibrium points, which is interesting. And we want to equilibrate the point and to keep it close to an unstable equilibrium point. So if you do nothing, it will move away. So you really need control. And the work consists, I give you the design of, I give you the linearized model, and you will have to do a feedback, a state feedback of the, to equilibrate the point, okay? So the state in this case is something that we have not yet discussed. Okay, what is your idea of what is a state? Can you tell me? Some of you? No ideas? Yes,
A definition of position, velocity, and acceleration of a system.
So Francisco says the state is position, velocity, and acceleration. Okay. Probably you are referring to a mechanical system.
Yeah, normally, yeah.
You can have, if you have a refrigerator, probably you have a temperature. You don't have positions. Okay. Okay. So any other opinions?
A state could be a set of variables that change over time.
Okay, so Eduardo is saying a set of variables that may change over time. That means that all variables that change in time are a state. More opinions? Okay, so the definition of state is what we are going to discuss to learn about in this course is a set of variables such that if you know them at one time and you know the future forces that act on the system, you are able to know all these variables for the future. Okay, let's test our definition. So suppose that I give you the initial position of the pendulum. Are you able, and I tell you what are the forces, and the forces in this case is just a force of gravity. Are you able to predict the exact movement? You write the equations, you know the equations, and you know the initial position. Are you able to integrate the equations of motion to find out the future values of position?
You probably need velocity too.
You probably need velocity. If you have a position, imagine that you have the pendulum in this vertical position as it is. It is not exactly vertical in this case, but it's more or less. Okay, so you have this position. Now you can have zero initial position, and it stands still. If you have zero initial velocity, and it stands still. Now, if you have a velocity that points to the left, okay, with the same initial position, the pendulum will move to the left initially. Then the forces can do some change, but initially it will move to the left. But if the initial position is pointing to the right, then the pendulum will move to the right. So you need the position and the velocity. Okay. Actually, we can say, well, do we also need the acceleration? What do you think? Or with the position and the velocity, if I know the initial position and velocity, I can integrate the equations and get the future values. Do I need the acceleration?
Yes.
You say Francisco is a brave man and he stands for this theory, which is a very good thing. Huh? Why do you say yes?
It wasn't me, Professor. It was another student.
It was another student, so you are innocent. Okay, sorry, Francisco. I saw
Me.
your microphone connected. Okay, it was João? Okay.
I said that because we can only know all the future positions through velocity and the initial position if the velocity is constant. Therefore, we need to know the acceleration.
I'm not so convinced with your arguments, but let me use another argument. Imagine that you neglect the mass of the rod. vamos desprezar a massa daquela barra. Okay, so we have only a mass at the top of the pendulum, material point. Okay, and if you want to write the equations, you use Newton's law. Okay, and Newton's law says the acceleration is equal to the sum of the forces. Now, what is this acceleration? If you have, suppose that your angle is theta, then you have theta dot is the velocity, and theta 2 dots is the acceleration. Okay. Now, if you want to write equations for theta, you have theta dot equal to velocity, okay, and angular velocity, let's call it omega, and omega dot, so the derivative of the velocity, which is the acceleration, is equal to the sum of the forces, according to Newton's law. So you only have two equations in position and velocity, you see? Because when you differentiate the velocity, you get the acceleration. So you don't need the acceleration. You just need two variables in this for these systems, these mechanical systems. Okay? So if you add the acceleration, it will still be a state, but it's a non-minimum state. You are adding something extra. Okay? And one thing that we are going to study in this course is conditions for the state to be minimal. And we are going to find out something which is a connection with a model that you know very well, which is transfer functions. And in transfer functions, you have zeros and poles. And if you build a state model for a transfer function in which there are cancellations of poles and zeros, then you will not have a minimum state. So you will have more states than needed. Okay, so the position and the velocity is a state. That's my conclusion. The position, velocity, and acceleration is also a state, but the acceleration is actually doing nothing. So you can get it, get rid of it. Sorry. Okay, was it clear? So the definition of state is a set of variables such that if you know them at some point, we know it for all other points. Okay, this is a very powerful notion that appears not only here in control, but in artificial intelligence, reinforcement learning, in many cases. Okay, so we are going to study this later, and so this is the project. You start with a model. You design the system. You design the controller with a model. Then you test it in simulation, and then either that's it, or if we are lucky and we can go to the lab in May, then you will be able to test your design in the real plant. Okay, so the laboratory is either just the initial part made of software and tests on simulation, which is interesting, but okay, it would be nice to test in the real plant, or if for known reasons we are able to go to the lab in May, then you will be able to test your design on the real plant with some small modification on your software. So this is the lab. Any question about the lab? Okay. Now this is when you see this word in bold: cyber physical systems that come from the interconnection of computers and mechanical and physical systems, in which you modify the characteristics the physical characteristics of the physical systems by computation. Okay, this is a very simple example. Okay, now let me tell you a story. I like so much this story that I even made a slide here. You see a number of bakers, and the story is this: in '75, you know that the Portuguese society was very much troubled. Okay, lots of political meetings and so on. And so in Técnico, a number of associations were asking space to do their political meetings, like unions. Unions are syndicates and other small parties and so on. So there was a professor called Abreu Faro. Maybe some of you have heard about him. He was at the basis of the renewal of teaching electrical engineering in Técnico in the 60s. And Professor Abreu Faro, he was teaching propagation of electromagnetic waves, so Maxwell equations, this stuff. And at the time, there was a course during the day and a course during the night for students that worked. And Professor Abreu Faro was giving the lecture in the morning, but his colleague who was teaching at night had some impeachment, so asked him to go and give a lecture. And he went there expecting to find about 15 students, and instead it was in the GAs downstairs. Okay, I don't know which one, either GA 1, 2, or 3. I don't know. I know it was downstairs. And he told that he arrived there and the amphitheater was completely full. People standing through the stairs and so on. All the places occupied. It was an incredible crowd of people. So he started giving his lecture. I don't know what was he speaking about, but you can imagine things related to mathematics of electromagnetic wave propagation. And after 15 minutes, everybody was silent, okay, listening to him. And after 15 minutes, one guy stood up and said, well, but is this the meeting of the Bakers Union in Portuguese? Mas isto é ou não é a reunião do Sindicato dos Padeiros? Okay? And he said, well, no, this is not the meeting of the Bakers Union. The Bakers Union probably is upstairs in the Salon Nobre. Okay, so everybody went away. The 15 students who should be there stayed, and he gave the lecture. So I think it's quite important that if you go listening to a meeting, that you know where or why are you there. So my question to you is, what do you expect to learn in this course, and why have you chosen the course? Probably why? Because you had no options. Okay, but apart from that, podem-me dizer porquê que escolheram este curso? Porquê que estão aqui e o que é que esperam aprender? No opiniões. No opinions?
Maybe because this course will give a more in-depth realization about control in general.
Okay,
maybe
so you
it's
want to improve your skills about control design.
yeah.
Okay. More ideas. If you want, you can say what you think in Portuguese, and then I will translate.
It's also to obtain a skill if we want to work with cyber-physical systems in the future. I think this is the most appropriate course.
Okay, Veronica says go in the directions of cyber-physical systems. That's an important thing. Yes. Yes. More ideas? Okay, so let me give you my idea. Well, I designed the course, and over the years, I have improved it a little bit. And my own idea is actually according to what you are saying. So you will have, the idea is to present a number of improved methodologies for controller design. Not just that, okay? And these methodologies, we are going to study 3 chapters, 3 of them devoted to control and 1 to modeling. These 3 chapters devoted to control will introduce you to very strong ideas in control. Okay, things like optimal control or Lyapunov theory, or even to linear control, linear state feedback. So, but all of them are, the guiding line is the notion of state. Okay, that notion of state that I discussed with you a few minutes ago. And of course, I also, and actually I wrote it, I also think that this is a very good way of introduction to cyber physical systems, because when you start control plays an important role in cyber physical systems. When you start interconnecting computers with physical system or a physico-chemical system, or even a biological system. So I use physics in a very broad sense. You will have feedback loops, and the idea of control is quite important here. The point is, what I would like to say more than you have just mentioned is that we are going to study methods related to this very powerful notion of state. Any comment? Okay, let's go. Let me give you one example. I mean, to do this example, you will need the techniques that you are going to learn here and a little bit more, because this is related to a humanoid robot control, and the difficulty is on modeling. Okay, you have many different parts. Actually, the model is quite complicated, but once you get it, you are able to design a controller using the techniques that you will study here. Okay? Of course, you would need some computer aided tools, design tools, because of the complexity of the system. Let's see one example. Probably you know something similar. Can you see the movie?
Yes.
Okay. So this is manufactured by a company known as Boston Dynamics. And you might say, well, but this is artificial intelligence. No, it's not. The controllers that allow you to do all this stuff are feedback controllers. And the type that you are going to study in this course. And it's model based. Okay, it's quite impressive. If you can later give a look, make a search by the keywords Boston Dynamics, and you will find striking videos. Okay. Sorry, Boston Dynamics is, I have to, it's my, let me stop this stuff. Okay. Okay. Now, we have already discussed this, but here you have some computation. So suppose that you have a small material point, say a magnetic sphere, and you apply a force by electromagnetic force. Okay, so you apply a tension to a coil around a core iron nucleus, and it attracts the force, the point, the ball, the small ball, which is subject to the force of gravity. Now, suppose that there is an extra force that I'm not representing here that corresponds to compensating the force of gravity. So the equations will be the mass times the acceleration, y is the position, so the second derivative is the acceleration, is the force u. Okay, so I'm canceling out the force of gravity. And then this is a second order differential equation. I say, well, the mass is 1, just to concentrate on the essential. Okay, so we have a second order differential equation. We have a second derivative. Now, you can define state variables as the position and the velocity. We have discussed that. And try to write differential equations for these state variables. Now, the equations are first order. Only the first derivative is involved. But now you have two equations. So you replaced a differential equation of order 2 by two equations of first order. Okay, and this is a state model. So the derivative of the position is the velocity. The derivative of the velocity is the force. Okay? One thing that we are going to study is how to convert models. For instance, I give you a transfer function, and from the transfer function you get a differential equation. That is very simple. Probably you know how to do it, but we are going to review it if you don't remember. And then from the differential equation, how to systematically write these equations. Okay, so you have replaced one second order equation by two first order equations, the state model. Okay, in general, in the linear case, you have a vector x, and you have a set of differential equations, of first order differential equations. A and B are matrices, X is the state, and U is the vector of manipulated variables, the so-called control variables, the things that you can impose from the outside. Okay, and then you have an output, which is a linear combination of X. So suppose that you measure just one variable, and so C is a row vector and X is a column vector. So this gives you a linear combination of the elements of X. So this is the model in the linear case. Later we will generalize this model to the nonlinear case. In the nonlinear case, we are going to say that this is just a function of X and U. Can be a nonlinear function. In the linear case, there are a number of properties about the solutions of this equation. And actually, the first chapter will be about studying this equation. Now, the state model is split in two parts. One part is this set of first order differential equations that models the dynamics of the system, okay, how it evolves when you apply a force. And the actuators. The actuators have to do with this B matrix. Okay, so the actuators, they are motors or power electronic devices, or something like that. And U are the signals that excite the system. So forces or certain commands for power electronic devices and so on. Something that you can manipulate in an easy way. And then you have this so-called output equation. So this is the dynamic equation, and this is the output equation. And the output equation is nothing more than something which is algebraic. It's just multiply a matrix C by X. Okay, so your model is defined by three matrices, A, B, and C. And this has to do with the sensors, okay? Because you measure Y, you don't assume you measure X. If you say, well, I'm measuring X, I know all the state, then C is the identity. Let me give you one example in which you cannot measure all the whole state. A glass oven, um forno de vidro. A glass oven is the closest thing I can imagine to hell. É a coisa mais parecida com o inferno que eu posso imaginar. Okay? So imagine a lake of molten stone, lago de pedra derretida. Okay? Where you have bubbles coming out because they force some air to bubble so that it becomes homogeneous. Okay? And then from this molten lake, you take a bit of molten stone and you produce glasses or glass objects of any kind that you want. Okay. And what is the state? The state is the temperature at any point in the glass stone, in the glass lake. Okay. So you can imagine that you have a grid of points inside this lake, and the state is the temperature at any of these points. Now, you cannot go deep into molten stone, and molten stone is above 1,500 degrees, much higher than that. Okay, so you cannot go there and place a thermocouple. A thermocouple is made of metal, and metal melts at, say, 800 degrees. So if you place there a thermocouple, it melts at 800 degrees, and you are going to place it inside something which is at more than the double of the temperature of the thermocouple. So it melts. So it's impossible to, okay? You can only read the temperature at the surface using, for instance, optical means. Okay, so this is an example, an extreme example, in which you cannot measure all the state variables. Okay, so Y is a vector in general. Y is a vector that has less components than X. Okay, so we have a different model, and this different model will be the basis for many things in our course. But why is it important to have this new model? Why not to live with the good old transfer functions that you use to design controllers using root locus and concepts such as phase margins and so on? The advantage is that, for instance, you can generalize it to the nonlinear case. And in the nonlinear case, you cannot have transfer functions. Later, we will discuss why. And furthermore, you can have several inputs. So you don't have just one input. U is not a scalar, but it's a vector. Okay, so you can have, say, 4 U's, 4 manipulated variables, and 4 output variables, but a state with dimension, say, 8 or 2 or whatever it is. Okay, so this model is quite practical to use with multivariable cases. So in the multivariable case, you can use this. In the nonlinear case, you can also generalize this. Okay, so these advantages with respect to the models based on the transfer function that you studied in your basic course on control. Any question? Okay. If some of you buy the book or have access to the book, I suggest you to read the pages 21 and 23 about general comments on this. Actually, the story, how we were led to using the state model is quite interesting. And it's related to space exploration. Okay, I'm not going to tell it about, but when it appeared, it was a kind of revolutionary concept. And during up to the end of the Second World War, control was based on transfer functions, the so-called servo mechanisms, using, for instance, to point or to move guns, os servomecanismos usados para movimentar canhões. Infelizmente, muitas das motivações são bélicas para grandes avanços da tecnologia e da ciência. But after the Second World War, there was a political strike, okay? And this political rivalry between East and West was materialized in the space exploration, sending spaceships to go around the Earth or eventually to the Moon. Okay, and there was a famous discourse of President Edward Kennedy of the United States, in which he said that before the end of the decade of the 60s, the United States would be able to send a man to the moon and bring it back alive. Okay, and actually this bet was well succeeded. And when you have a spacecraft, then Newtonian mechanics provides you very good models. And in many cases, you have linear models. So much of the theory was boosted by this quest for putting a man on the moon, okay, in the United States. Now, let me tell you a little bit about the course objective. So the big objective is, you can write it in one line, is use state models to obtain methods for analysis and design. Okay? And actually, we are going to study 4 big parts. The first part is about the linear state model analysis. How can I convert models? Say, I give you a transfer function and you compute a state model, or I give you a state model and you compute the equivalent transfer function in the linear case. Okay. Now, notions related to minimality. You see these words: controllability, observability. This is related to the capability of from Y estimating from the output, estimate the state variables using things like state observers. They are basically state estimators from Y, or to accomplish or to solve certain control problems, move the state from one value to another value. Okay, it's related to these important notions of controllability and observability. And also the time response. So more than computing the time response, it will be important to study the structure of the time response. And this will equip you, will give you some weapons that are very powerful in this response, as giving a qualitative answer. So the first chapter is about analysis of linear state models. Then the second chapter is using state variable feedback. No, so not just feeding back the output as you were doing in the classical control course, the basic control course, but feeding back all the state variables and to design your controller. Okay, and in cases where you don't have access to all the state variables, estimate the state variables, and we are going to study an important theorem that separates both things, allow you to design separately the state estimator and the state feedback. Okay, and then you feedback the estimates. That's a separation theorem, quite important. Okay. Then in chapter 3, we are going to enter the nonlinear case, and we are going to study one thing, which is Lyapunov's Lyapunov direct method to study stability, and not just to study, but also to design controllers, including adaptive controllers, that is to say, controllers that you don't know a priori some of the parameters of the system, and these controllers are able to adjust an estimate of this parameter. Okay, that's adaptive control. You learn by looking what happens when you excite the system and you observe the response, and you infer the value of the parameter, so you optimize your control law from that. And we are going to study this technique, which is a very, very powerful technique. It's the basis if you want to design controllers for aircraft or in robotics. This is an essential thing. And finally, optimal control. Okay, in Pontryagin maximum principle. Okay. So what is optimal control? Suppose that you have a robot that when you want to move it from one point to another, and you say, I want to go from this point to that point by minimizing the energy that it spends. Okay, and so you have to optimize with respect to a control function. This is an optimization problem. Usually you are familiar with optimization problems in which you want to optimize a function with respect to a vector. Okay, so you compute the derivatives of this function with respect to the elements of the vector, and you equate these derivatives to 0. Okay, but here you are not optimizing with respect to a vector. It's to a function. A function, you can think of it as a vector with infinite elements. So a function is defined by infinitely many points. So how can we solve these infinite dimensional optimization problems? That's a completely new idea with respect to what you have studied before. And the tool is this Pontryagin maximum principle that appears in the 50s. Okay, so this is what we are going to study. Any question about this? Let me spend some minutes giving you a number of examples of problems that we can solve. This is a list, and you can later see it with more care on the new things that you are going to learn in this course. Okay, and some of these things, if not all of these things, are among the most important concepts of control engineering. You have Lyapunov's direct method to study stability of nonlinear systems and even to design stable nonlinear controllers. Pole placement by linear state feedback, so imposing the poles by linear state feedback, and estimating the state with the Kalman filter. So Kalman filter is one of the most striking inventions of electrical engineering, not only of control engineering. Pontryagin maximum principle, multivariable control, and a glimpse of adaptive control based on the Lyapunov's direct method. Okay, so these are maybe the main new things that you are going to learn here. Okay, you can see here some of the characters that allow us to give this course. Lyapunov, Kalman. Kalman died quite recently, okay? Bernoulli, okay? Bernoulli, well, 3 centuries ago, more than 300 years ago, he posed this problem. Suppose that you see this picture here, you want to go from this point here at the top to this point here at the bottom on the right. And you want to slide. So imagine that you have a bed. A bed is a small sphere with a hole, and you put it on a wire and you let it slide without friction. And the problem is very simple. What is the shape of the wire that makes the bed slide from this point to this other point in minimum time? Okay, that's a so-called Brachistochrone problem. Okay, chrone is related to the Greek word which means time. In brachistos is related to minimum. Okay, so minimum time problem. Okay, now we have a problem because we have to adjust this function. We have to adjust this function, and Bernoulli placed this.
Não, Luciano não quer vir, mas valia termos ficado no outro.
Diz? Foi uma mensagem espúria. Okay. So we have this. The problem of optimizing the time as a function of the shape of this function. Okay, so if you have infinitely many shapes, here you have 3. Actually, it's not difficult to conclude that you can do much better than the straight line, because if you accelerate it more at the beginning, you will go faster and you will have a smaller time than with just a straight line. Okay, but what is the optimum? What is the optimum? Because you are increasing the length, so there is probably some compromise. How can you compute it? And Johann Bernoulli made a challenge to the scientific community. A number of people answered. And this cave was the origin of a very rich story that started with oil. Actually, I'm being very, I'm omitting a number of important names, but Euler with the variational calculus, Lagrange with the analytical mechanics, and finally Pontryagin with the principle to solve optimal control problems. In the beginning, you had no control variable, but you can later include control variable. Now, let me give you a challenge. I won't answer it here, but you can think about it. How can I transform this problem into a control problem? So what is the manipulated variable that I can define in the dynamics of the system? Okay, you can think about that. Okay, now a couple of examples. I selected them to be quite different. I also select some examples in which I was personally involved, but this was just for fun. So one problem, optimizing or controlling the distribution of water. So you have a water canal, a water distribution canal. So the water starts from here, and you have a number of pools, so stretches of the canal. Tem canal com vários trechos do canal. And you have a number of gates, okay? You have a number of gates. And you want to operate these gates such as to keep constant the levels here at position 1, 2, 3, and 4. So you have 4 manipulated variables, U1, U2, U3, and U4, that corresponds to the position of the gates. When you close the gates, you have no water passing. And you have 4 manipulated variables. Okay? Now, here you have an experimental canal in the University of Évora. This is a unique facility in the world. There are 2 more facilities like this, one in Barcelona and the other in California. But this is much alike. This is small, 150 meters, but this is much alike and uses the same equipment as you can find in Alqueva or many other canals in the world that you use to bring water, for instance, for agriculture. So you have a number of offtakes, you have a number of disturbances here, you see. These valves simulate farmers that use water and create disturbances. So the problem is, how can I manipulate these gate positions to impose, to keep still the levels at this, just before the gates? That's one possible problem. There are other problems related to this canal. Now, you can say, okay, very simple. I put here a PID controller relating Y1 to U1, another PID relating Y2 to U2, and so on. Let's see what happens. These are experimental results. And the blue line is the set point, and the green line is the levels. And you have 3 levels. J1, J2, and J3 are levels. And everything is under control. And then you say, well, I want to increase my set point in 5 millimeters, okay, which is quite specific. And what happens? Well, it goes there with a transient which is not so beautiful, but it goes there. It causes some disturbance on the other 2. Here I had also a different, an increase of some millimeters that causes this disturbance here. Now, I say, okay, let's increase again 5 centimeters. 5 centimeters. Okay, 5 centimeters. And this is quite specific. But you see what happened? It starts oscillating. Everything started oscillating. And at this point, the system had some protection that forced the system to shut down because it became unstable. Okay, the motors were widely. I'm not showing the manipulated variables, and you can see the motors here. Okay, I'm putting my hand there because to show that the motor is cold, although it is in operation. If it starts doing maneuvers like this, the opening and closing, the motor becomes very hot, and there is a thermal protection that stops the motor. Also, the level of the water here was close to the border, and you want the water not to overspill. So with separate PIDs, you got an unstable system. Okay, this is the type of system that you have, for instance, in Alqueva, by the way. Now, suppose that you have a multivariable controller designed with the techniques that you are going to study in this course. Okay, and you can see that before you were operating for about half an hour. So this is time in seconds. So you have 1 hour is 3,200 seconds. So this is a little bit more than half an hour. But here you have 10,000 seconds, so 3 hours, something like 3 hours. And it's operating and going and going and going. Okay, so I have examples for a whole day of operation. Not a whole day, but a whole night, say 11 hours and so on. Okay, and this uses the techniques that you are going to study. Okay, a problem in telecommunications related to observers, to state observers that we are going to study. Inferring the state that is to say the position and velocity of a satellite or a position from a number of observations. So from Y observe X, we are going to study that problem too. Another set of problems that we are going to consider later, which is quite actual, is controlling the temperature in solar thermal fields. Later we are going to speak about it. And finally, controlling anesthesia. So you have a patient and you want to control the level of paralysis of the patient. So anesthesia is not only about making the person becoming asleep, but also, and for that you can also have a controller, but also preventing that the person has involuntary movements. So for that you measure the muscular activity. There is a sensor here in this hand. You see these electrodes, they are connected to some instrumentation tower that measures the muscular activity. And then you have an actuator, which is this steering connected to a computer. And if you can recognize here the screens of MATLAB, okay? So you measure the muscular activity, then you have a controller implemented in MATLAB, and you give an order to the steering, okay? You can also do it with the level of loss of consciousness, okay? So 100 is the way in which we are, wake up, okay? 0 is deep coma, and you want to drive the person to a place of loss of consciousness, of self-consciousness, which is about 50, okay? So you are manipulating the rate of administration of a drug using a syringe here, and such that you are close to this set point at 50, okay? So this blue line is the measurement using the EEG of the level of loss of consciousness, the degree of in which the person is asleep, let's say in rough terms. And you can design these controllers using the techniques that you will study in this problem. Okay, finally, optimizing the control for C-wave energy. That's another important example. Okay, so I could have given much more examples. The idea here was to show you that the controlling this course provides essential tools to tackle engineering problems in many, many different areas. The final slide is just that I would like to stress that the emphasis of the course is on mathematics, but we want to put knowledge, that is to say mathematics, in action. So mathematics is not just presented for the mathematics, but for its engineering context, okay? There is this sentence of Boltzmann, who developed the theory of gases. There is nothing more practical than a good theory. So that's what I would like you to feel at the end of the course. Any final comment or question? Okay, if not, we stop here. Thank you very much for your attention. And we will see each other Friday.